Far from any mainland, a hidden reef lies beneath restless tropical waters.
Here, powerful currents and violent storms make permanent construction nearly impossible.
A fortress built from the seabed. Today, we follow an extraordinary concept.
The finished complex would combine aviation, maritime logistics, communications, and coastal protection.
But before construction begins, engineers must first understand the ocean beneath them.
The reef's edges fall away abruptly, leaving little natural support for reclamation.
Strong subsurface currents could carry loose fill away before it ever settles. Every unfinished surface would remain exposed to waves arriving from multiple directions. Every worker, machine, fuel tank, and structural component must arrive by sea. The central question is simple. How can engineers build land where none exists?
The surrounding sea lane carries intense traffic but offers almost no emergency infrastructure.
Without a nearby harbor, repairs, refueling, and medical support require long diversions.
Aircraft operating far offshore also depend on distant bases and narrow fuel margins.
Planners propose a self-sufficient platform combining harbor, runway, power, and communications. Each zone must operate independently while remaining connected through one protected infrastructure network. A sheltered port would create a permanent lifeline for fuel, equipment, and personnel.
A full-length runway would extend operational reach and provide emergency landing capability. Communications systems would monitor weather, navigation, and regional maritime movement.
Because the island is isolated, power, water, and waste systems must be self-contained.
The project must convert an unstable reef into a durable, operational platform. Survey teams begin by tracing the reef boundary with satellite-guided navigation.
Multibeam sonar measures thousands of depth points across the seabed every second.
The resulting map reveals ridges, channels, slopes, and possible foundation zones.
Divers mark critical boundaries where temporary containment berms may later be formed.
Sensor buoys record wave height, current direction, salinity, and tidal variation.
Core samples determine whether underlying limestone can support the reclaimed platform.
Layers of coral sand, fractured limestone, and compact rock are carefully documented.
Loose particles are evaluated for drainage behavior, settlement, and resistance to erosion. Decades of storm records define the wave forces the island must survive.
The eastern slope experiences concentrated currents capable of stripping away fresh fill.
Engineers discover that one proposed edge sits beside an unexpectedly deep channel. The survey confirms that reclamation is possible, but only with strict containment. Conventional dumping fails because waves disperse loose material before compaction can begin.
Unlike dry ground, the reef provides no broad, stable platform for ordinary foundations.
Millions of tons of reclaimed material could settle at different rates. Even small differential movement could damage a runway built to tight tolerances.
The vulnerable construction phase is more dangerous than the island's final operation.
Long supply routes also expose fuel, machinery, and components to weather delays.
Placing massive rocks accurately becomes difficult when both crane and load are moving.
Saltwater corrosion threatens reinforcement, machinery, electrical systems, and exposed structural connections.
The runway must align with aviation requirements without weakening the protective shoreline. A poorly positioned harbor entrance could channel destructive waves into the protected basin.
Every solution affects another system: shoreline, runway, harbor, drainage, and logistics.
The project therefore requires one integrated design rather than separate structures. The design team evaluates elevated, floating, and fully reclaimed structural alternatives. A piled platform would demand excessive steel, specialized drilling, and constant corrosion maintenance. A floating base cannot provide the stiffness required for a long, permanent runway. The selected solution uses compacted fill restrained by a continuous armored perimeter.
Multiple layers progressively filter, support, and protect the island's reclaimed interior.
Graded filters prevent fine sand from escaping through gaps between larger stones.
Interlocking concrete units dissipate wave energy while resisting displacement during storms.
A gentler outer slope reduces impact by forcing waves to break gradually.
Offset breakwaters prevent direct ocean swells from entering the deep water harbor. Preloading and vertical drains accelerate settlement before concrete pavement is installed.
Marine concrete and protected steel extend structural life in the salt-saturated environment.
The final design prioritizes perimeter protection before vulnerable interior construction.
Construction begins with a floating industrial fleet assembled far from shore. Heavy anchors secure vessels against currents while maintaining navigational clearance.
Temporary service barges provide fuel, repairs, storage, accommodation, and emergency support.
Every worker receives flotation equipment, radio contact, and personal GPS tracking. A buoyed safety perimeter separates construction traffic from passing vessels.
Flexible pipeline sections will carry dredged sand directly onto the reef. Low containment berms create calmer water for the first controlled fill placement.
Tracked machines form temporary roads using wide mats that distribute their weight.
Temporary power and communications connect marine crews with the remote command center.
Local forecasting equipment provides earlier warnings than distant regional stations.
The reef now supports a temporary base, but permanent land still does not exist.
Far inland, factories begin producing components too complex to fabricate offshore. Prefabricated steel modules reduce assembly time in the corrosive marine environment. Reinforcement cages control cracking while marine concrete resists saltwater penetration.
Each armor unit is cast with geometry designed to interlock under wave loading.
Mechanical vibration eliminates voids that could weaken the concrete during repeated impact.
After controlled curing, every unit receives an identification and inspection record.
Quality control now determines whether these components can survive decades at sea. EMA checks for internal voids, cracks, and inconsistent material density.
Concrete samples must exceed the specified compressive strength before shipment. Steel coatings are measured precisely to ensure complete corrosion protection.
Trial assembly confirms that bolt holes and connection plates align correctly.
Sensitive equipment is enclosed against vibration, moisture, and salt exposure.
Special cradles distribute weight and prevent movement during the long sea voyage.
Shipments leave only when forecasts provide a safe offshore transport window.
The main reclamation begins as dredgers collect suitable sand from approved zones. Pumps lift the mixture into storage while monitoring density and particle size. The slurry spreads slowly, allowing heavier sand particles to settle first.
Excess water returns through controlled outlets while the reclaimed surface rises.
Bulldozers shape each lift before deeper material can compact under its own weight.
Vibratory rollers increase density and reduce future settlement near the surface.
Deep vibration rearranges loose grains into a stronger, denser foundation. Sensors track vertical movement as the new land consolidates under increasing load.
Extra weight forces long-term settlement to occur before pavement construction.
Graded stone begins forming the protective boundary around the sand core. Machine guidance positions each rock within the engineered seawall profile.
Heavy armor units create an irregular surface that breaks incoming wave energy.
Divers confirm that hidden gaps do not expose the filter layers beneath.
With every completed section, the interior becomes calmer and easier to develop.
A separate dredging operation creates sufficient depth for large supply vessels.
The entrance follows a curved alignment that blocks direct ocean swell.
Only after settlement stabilizes can the rigid runway pavement be installed.
Guided equipment maintains strict surface elevation and cross-slope tolerances.
Controlled joints accommodate thermal movement without random structural cracking.
High-strength bolts connect the curved frames to deeply anchored concrete bases.
Prefabricated tower sections rise quickly, reducing exposure to salt and weather. The island now resembles a facility, but its perimeter remains partly unfinished.
A tropical system unexpectedly intensifies before the outer seawall is fully closed.
Jack orders immediate suspension of dredging and exposed lifting operations.
Ryan activates the evacuation plan for teams working near the vulnerable shoreline.
Tugs move support vessels away from open water before conditions become uncontrollable.
Ocean energy concentrates through the unfinished opening like water through a nozzle.
The accelerating flow begins eroding the island's unprotected interior edge.
Instrumentation records rapid material loss near the future runway shoulder. A section of temporary roadway fails, cutting access to the eastern perimeter.
The crisis is not general settlement. It is concentrated flow through two openings.
Unless those breaches are closed, the storm could dismantle months of reclamation. Liam prioritizes the openings generating the strongest erosion currents.
Modeling shows that a broader, lower slope would dissipate more wave energy.
Echo Sierra units, winds are picking up. Secure your load and deploy immediately. Secured, moving out now.
Rock-filled gabions provide immediate mass while conforming to the damaged seabed. Crews place the first emergency barrier when wave height briefly decreases.
Armor stone strengthens the temporary closure and prevents individual baskets from moving. Reserve concrete units complete the outer surface and disrupt incoming waves.
The revised geometry spreads impact across a larger, more stable footprint.
Airborne laser scanning measures erosion, settlement, and repaired seawall elevation.
Sonar confirms the foundation remains continuous, allowing construction to resume safely. Protected cable networks distribute power without exposing critical systems to salt spray.
Solar generation reduces fuel consumption during routine island operation.
Redundant generators maintain essential services whenever renewable output becomes insufficient. Reverse osmosis systems convert seawater into drinking and industrial process water. Oversized drains remove tropical rainfall before water can compromise pavement foundations. Backflow valves prevent waves from forcing seawater into the drainage network. Protective radomes shield rotating antennas from wind, salt, and heavy rainfall. Independent communication paths provide redundancy if one network becomes unavailable. High-pressure fire protection covers the island's most hazardous operational zones.
Integrated monitoring transforms separate structures into one coordinated operating facility.
Static and moving loads test pavement strength and remaining foundation settlement. Surveyors verify elevation, slope, alignment, and smoothness across the entire runway.
A simulated cloudburst tests drainage speed and resistance to surface ponding.
The drainage network clears the runway without allowing seawater to return.
Load testing confirms that quay structures and cranes meet operational capacity.
A navigation trial verifies channel depth, turning clearance, and wave protection.
Fire pumps deliver simultaneous pressure to multiple sections without significant loss.
Critical radar, lighting, drainage, and communications remain active during power loss.
Night testing confirms visibility, signal accuracy, and reliable approach guidance. Every structural and operational system now meets the project's concept requirements.
The island enters operation as its deepwater harbor receives the first support ship.
The curved entrance keeps ocean swell outside while guiding vessels into calm water. The harbor immediately begins sustaining the island's isolated workforce and technical systems.
The first aviation trial demonstrates the stability of the reclaimed runway foundation.
For the first time, every major system functions together under full operational conditions.
From a reef hidden beneath the waves, engineering has created land where none existed.